So today we're gonna see more applications of entropy methods. Last time we'll see two short applications. One is the special case of Kruskal-Katona, the triangle maximization problem. One is the triangle intersecting family, both using Schirer's lemma. So today we're gonna see some more. The first one we're going to talk about is the permanence of a matrix, which has equivalent form as perfect matchings in bipartite graphs. This is the well-known, well, by now, well-known theorem of Bregman. So let's see this. Okay. Bregman's theorem. Let's first, it has two equivalent formulations. Let's see the first formulation, the permanence. So definition. The permanence of an m by n matrix A is nothing but the sum over all permutations in the symmetric group on n elements, the product of the transversal corresponding to this permutation. Okay. Now, this is kind of like the determinant of the matrix, but the signs somehow get forgotten. That makes all the differences because for determinants, there's an efficient algorithm to compute it, but for permanents, just because of the difference of the signs, it's computationally difficult to determine the permanence. So now let's see an equivalent way of viewing permanence as perfect matchings. So there's an equivalent way. Which is perfect matchings in some bipartite graph. Okay, so how do we do that? Let me show an example. Let's see this very special 5 by 5 matrix. Let's see a small example, 5 by 5 matrix. And let's always restrict throughout this course, we're gonna look at 0-1 matrices, okay? Zero-1 matrix. Let's say our 0-1 matrix is like this. Okay. Now what we're gonna do is we're gonna view, we're gonna index the rows. Let's say the rows is U1, U3, U4, U5, and the columns are V1, V2, V3, V4, V5. Then we can view this 0-1 matrix as the bipartite we can view it as the bipartite adjacency matrix of a bipartite graph. What does it mean? We have a bipartite graph with vertex at U consisting of this U1, U2 to U5, and we have another part, which is V, consisting of this V1, V2, V3, V5. We have an edge between UI, VI if you have a number 1 there. And there's no edge between the corresponding UI, VI if it's 0 there, UI, Vj. Okay? In this case, this matrix is nothing but just a perfect matching. Let's see, U1, let me draw this graph. Let's draw it together. So U1 is adjacent to V2. So it goes here. U2 goes to V1, like that. And then U3, U4, U5 kind of shifted by 1. So U3 goes to V4, U4 goes to V5, U5 go back to V3. This is the corresponding graph. And well, if you look at the permanence, we take a product over a transversal, I and sigma I. Here, all the transversal, if you take the product, it will be 0, unless you take this particular transversal, this particular transversal corresponding to the permutation sigma. And in this case, each one in 0, 1 matrix, in other words, each one of these summon correspond to a perfect matching. And when you sum up over all possible transversals, the permutations, we get all possible perfect matchings in a corresponding bipartite graph. This is what we meant up there. Okay, so we can now state Bregman's theorem, which offers an upper bound on the permanent of a 0, 1 matrix. In other words, it offers an upper bound on the number of perfect matchings in a bipartite graph. So Bregman's theorem offers an upper bound on the permanent of 0, 1 matrix, which is the same as the number of perfect matchings in a bipartite graph. The statement goes as follows. Bregman, let A be a n by n. We have A, n by n 0, 1 matrix with row sums D1, D2, to Dn. Row sums just means the number of ones in each row, okay? And look, what does row sum means? The number of ones in the first row is the number of neighbors of U1 in V. So it's exactly the degree sequence of one part of this bipartite graph, okay? Let's keep that in mind. So this is the degree sequence of vertices in one part of a bipartite graph, where this bipartite graph corresponds to this 0, 1 matrix. Okay. Then we have the conclusion is the permanent of A, which equals to the number of perfect matchings in the corresponding bipartite graph, is at most the product I goes from 1 to n di, the degree of the i's vertex, or the i's row sum, factorial, raised to power 1 over di. Looks like a strange number, but let's first argue that this bound is optimal. You cannot improve it. We cannot guarantee that the permanent of a zero-one matrix is smaller than this number. So we need to give an example where equality holds. So I'll remark this bound is optimal. Why? Well, the type example is you assume D divides N, it's a divisor of N, and consider an M by N bipartite graph, which is disjoint union of N over D KDD. Okay, look something like this. KDD, KDD. You take N over D many. Oh, maybe I should write it like this. Each one is a KDD, and we write it vertically. Okay, so we have one part n vertices, another part n vertices. In total, n over d many. All right, let's see what is the number of perfect matchings in here. Well, the number of perfect matchings equals to the number of perfect matchings in a KDD in here, right? And then raised to power n over d. Raised to power n over d. And what's the number of perfect matchings in KDD? You can take any permutation, it gives you a perfect matching. So that equals to d factorial n over d. Okay, and look at this number. In this particular graph, every vertex has degree d, so it's d regular. So all bi equals to d. So we have d factorial raised to 1 over d, and you take the product n called n times. Every term is the same, forget about the product, it's exactly this guy, which is the thing we get here. Now let's think in a permanence language, what is the corresponding matrix? The corresponding matrix looks like this. KDD is just the matrix where, how does it look like? KDD, well, this is D vertices U, D vertices, just all one matrix, right? This is K33. And we have a block construction here because you take this joint copy. So it looks something like this. Da, 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 da. You have n over d blocks. And here are all one matrix. The other part is 0. Okay. This bound is optimal. So how do we prove it using entropy? As I said, now let's forget about the permanent formulation. Let's just look at bipartite graphs. So Bregman's theorem, once again, for bipartite graph says that if you have an m by n vertex bipartite graph with degree sum, with degree sequence d1 to dn from one side, then the total number of perfect matchings is at most this number. And to bound the number of perfect matchings, this set, what we're going to do, usually we're going to do is we're going to uniformly random sample perfect matching from the set of all perfect matchings. And we can associate the number of perfect matchings to the entropy, which is log of this size. And our goal is reduced to upper bound the entropy of this perfect matching. And if you think about it, the perfect matching, if you randomly sample a perfect matching, the ends of the left-hand side points are just some random vertex on the right-hand side. So we can sort of write this perfect matching, random perfect matching in the vector form, and somehow use additivity, some convexity thing to upper bound it. That's exactly what we're going to do. Proof. We prove so we're gonna let G be an m by m bipartite graph with parts U and V, each of size n, such that the degree sequence of U is d1 dot 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 dn. Okay, let M be the set of all perfect matchings in G. Our goal is the cardinality of M is at most product of this di factorial raised to power 1 over di. I goes from 1 to n. And so we're going to do our usual trick. We're going to sample. The starting point is we're going to sample a perfect matching, a uniform random perfect matching from the set of all perfect matchings. Here's a picture. So here's U, here's V. This is our vertices, U1, U2, UN, right? The degree of U2 is D2. And the perfect matching, if this is our sigma perfect matching, we can call this sigma U2, sigma U1, right? Sigma UN. It corresponds exactly to a permutation. I sends to sigma UI, the index of this vertex. So think of this as a random permutation of the right-hand side. What we need to do now, since sigma is uniformly generated by maximality, the entropy of sigma is nothing but the log of size of its space of values where sigma takes, which is m. And now our goal, new goal, is to prove that this is at most, let's take the log there. So it's sum over all I log di factorial over di. Okay. All right. Let's first what we're going to do is we fix an ordering of the vertices from the left-hand side. Let's fix the ordering, not necessarily this U1 to UN, all right? Just an arbitrary ordering of vertices. So first, fix an ordering. So what we're going to do now is we're going to think of how we can generate the perfect matching. So you fix an ordering, and we look at how many choices of the first vertex it can be mapped to. You choose one of its neighbor as the first edge of the perfect matching. And you look at the second one in the ordering, and look at one of its unused neighbors, and match it to that one of those neighbors, and continue. And let's see, in this way, how many perfect matchings we can generate. Fix an ordering how U1, which I also call U1 to UN of U. Now, now we can think of, that means we can view sigma, this perfect matching, random perfect matching, as a random vector, which is sigma U1, sigma U2, what I just said, sigma UN. Okay. Where sigma UI is the other endpoint of the matching edge in sigma containing UI. Now we can use chain rule to expand the entropy of sigma. So chain rule says that this is what H, oops, let's write it in vector form, is the sigma UN. By chain rule, this equals to, I first review where the first vertex U1 in this ordering tau goes. After reviewing that, now we review where the second vertex goes. But this new information is on top of what we already know about U1. All the way till the last one, which is H of sigma UN, given all the previous one. Sigma U1, sigma UN minus 1. Oops, I cannot fit in here. Plus H of sigma UN, sigma U1. Okay, nothing but chain rule. Now, let's look at how each one of these look like. This conditional thing looks like. Let's fix it. Let's look at VK, UK. After, one thing we should notice is, at the time of UK, we've already reviewed the image of U1 to UK minus 1. So after revealing, for this conditional entropy, after revealing sigma U1 to sigma UK minus 1, where UK can go, the other endpoints can only take value in the set of unused neighbors. What does it mean? We cannot use, this is nothing but n of UK. UK has to be mapped to one of its neighbor, but we cannot use any of these vertices. Right? Unused neighbors. Let's define a parameter that equals to this set, the set of unused neighbors, after revealing this. D tau sigma of VK. So what does this mean? We first fix tau, which is the ordering of U. After fixing tau, we know how V1 to Vn looks like. So Vk is now meaningful. We're gonna, in this case, sigma is random. In this case, sigma is random. Keep in mind. This is the number of such unused neighbors. And remember, this number of such unused neighbors itself is a random variable. This is a note. This is a random variable because it depends on, depending on sigma, which is random. Okay. Good. So, but what do we know? We know this graph, we know the degree of, this should be UK. We know the degree sequence of the vertices in U. So that means we know the total number of degree neighbors of UK. If we reveal what this is mapped to, what this is mapped to, we also know what's this guy, then this number becomes a constant. If you reveal, fix this value, this random variable becomes a constant. Okay. So we can now bound this conditional entropy. How do we bound it? Let's write down this conditional entropy, sigma UK, conditioning on U1 sigma UK minus 1. Conditional entropy, let me use a shorter form. If you write this as X, this whole tuple, K minus 1 tuple as Y, remember, this is conditional entropy, right? By definition, it is the sum. By definition, this is the sum of Y equal to B, choice of B, and probability that Y equals to B, conditional entropy of Y equals to B, right? Or in other words, sigma B sigma B, did I write it in terms of B? Give me a second. What notation did I use? Oh, okay, this is fine. H of X, Y equal to B. All right. But what is this? As I said, if you fix a particular choice of each one of these, this guy becomes the number of choices of sigma UK must take value in a set of size this much. By maximality, then it's at most and maximality. This is at most sigma b. Now x takes value here. So it's log of the range, which is d tau sigma uk. Okay. And this b basically depends on sigma, right? B is sigma. This is just expectation of sigma log of tau sigma uk. All right. We can now write this conditional entropy in this way. Now we're going to sum them all up. We can write entropy of the original random matching. So H sigma equals to sum this all up for all k, which is, but now it's inequality, right? So it's at most sum of this expectation. Let's swap expectation and sum. So it's expectation over sigma sum I from 1 to n log of OK using this k. D tau sigma uk. All right. Any questions so far? Now we need to estimate this guy. The problem now is that if we fix tau for a given tau, when sigma is uniformly random chosen from the set of all perfect matchings, we don't have much understand. We cannot get a control on this number of unused neighbors. It's very hard to analyze. So the clever idea is that to introduce another layer of randomness. So for a given tau, hard to analyze this. The idea here, clever idea here, is introduce another layer of randomness. In particular, we're going to sample tau also randomly. By this, even though for a particular tau, it's hard to analyze it, but if you sample tau uniformly at random, we can at least understand the behavior of these parameter unused neighbors in expectation on average. And the result is we know how this thing behaves on average. All right, so let's carry out this idea. Now let's fix a sigma and try to randomly and uniformly sample tau. Now we're going to sample tau uniformly at random from all permutations, all orderings of the vertices of U. So it's basically tau itself is a uniform random permutation on n elements. So this is, since we fixed tau, all we need to do is to look at here. Now we're going to look at the contribution of each vertex towards this sum. As I said, let us consider the contribution of each vertex U in U towards the sum, this. The claim is when tau, the claim is as tau is uniformly sample, is uniform, this number of for each VU in U contribution, for each U in U, if you look at this term, the number of used neighbors of U is uniformly distributed over this set. In other words, if U is this UK, the kth one in the order, then this d tau sigma UK distribute uniformly over the degree of UK sets. Right? If this is UK, the number of used neighbors somewhere between 0 to degree minus 1. So the number of available one is somewhere between 1 to everything, which is this set, uniformly sample over this set. So we're going to prove this later. Let's first see how this claim finishes the proof. Assume this is true. If this is true, claim implies the theorem. This is because this is the contribution, right? Now let's look at this inequality. This is the contribution, and this is true for any sigma. We fix the arbitrary choice of sigma. Okay. Then that means if you take the expectation over tau, now tau is random, this sum that we cared about, log d tau sigma UK equals to, what's the contribution? Well, we have to sum over all vertices in U, sum over all vertices in U, and look at their contribution. Their contribution is this. The number of unavailable neighbors distribute uniformly random over this set. So that means with probability 1 over du, this value takes anything between 1 to du. So each one is equally likely 1 over du, sum over log of 1 over di. Sorry, 1 over I goes from 1 to du. Okay, once again, the contribution of this to this guy with probability 1 over du, it takes value I for any I between 1 to du. This is what this means. So you sum up all these, we get this one. Okay, now you just need to simplify it. Equals to sum over, what is this? This is nothing but log I, right? I made a mistake here. Yeah, look at log of the available neighbors. So log I. Log I for I to du, this is nothing but log du factorial. Over du, sum over everything. So that's precisely sum over log di factorial over di. Okay. This holds for any sigma that we fix. Since this holds for any sigma we fix, you take another expectation, we get that. So this shows that expectation of sigma, expectation how sum over this quantity also equals to the same thing. That means there exists a tau such that this guy is at most this expectation. First moment method. But remember, what is this guy? This guy is nothing but an upper bound on H sigma. So we have H sigma. And that's our goal at the beginning. We want to prove this, right? Conditioning on this claim. So let's now prove this claim. This I'll just prove it by sort of by picture. So we have U fixed, right? Here's a picture. Let's say we fix U to be this guy. This size capital U, this size capital V. And in this scenario, we have sigma fixed here. Here, sigma is fixed. So the perfect matching is fixed. We have, let's say this sigma is green. Sigma is fixed, so this guy goes to here. Let's say this guy goes to here, 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 the same. I just draw. I don't link all of them. I draw some of them. Okay. Now, tau is random. Here, tau is random. What does it mean? That means we don't know the ordering of U1 to UK is random. The ordering on the left-hand side is random. Again, but we know if you fix UK, we know which edge is mapped to because we know sigma. So we do know, let's let Yj to be sigma Uj for every j in n. Okay, that's the other edge, the other endpoint that's mapped to. Actually, let me also draw these as if this is ordered. Let me draw U according to the ordering of tau. I reshuffle U so that U1 goes on top. But I don't know which guy is this guy. It's U something, okay? We don't know its position. This is UN. Now, in this picture, right? So this is, in my picture, Y1. This is Y2. Am I doing correctly? Give me a second. No, sorry. Oops. Let me redraw this. I meant something else. So here's U, here's V. We fix the vertex U in capital U. All right. Sigma is fixed. So the perfect matching is fixed. Tau is random. We don't know the ordering. Which one is U1, which one is U2, which one is UN on the left-hand side. We just first look at all neighbors of U. This is neighbors of U. It has DU neighbors. Let it has D neighbors. Each one of this neighbor, since sigma is known, so where this guy is mapped to in this perfect matching, we know. So this guy, right? This guy, this guy. Let the neighbors to be V1 to VD. And sigma inverse the other endpoints of Vj Let me think. I see. Okay, so let's always be clear what is fixed. U is fixed here, sigma is fixed here. Okay, what it means is that this is also fixed. We know Vj, j from 1 to d, which are the neighbors of U, are fixed. So that means sigma is also fixed, this green matching edges. The other endpoint, this is sigma inverse of Vd, are also fixed. These are all fixed. Now, let's look at the relative ordering of the pre-image of Vj. The ordering of sigma inverse of V1 to sigma inverse of Vd is a restriction of the tau on this set of d vertices itself. Because tau is uniformly sampled, this restriction on this d vertices is also uniformly sampled. This ordering is uniformly sampled over all d factorial permutations. Is uniformly distributed over all d factorial choices. Okay, what does that mean? That means if let's look at the position of U, right? U is in this green sigma edge is linked to some of its neighbor, let's say Vi. Now, if V equals to is mapped to Vi, then we need to look at the position of this inverse of Vi in this sequence of D sets, in this set of D vertices. You look at this position. If it comes first, that means no previous neighbor is being used. If it comes last, that means all the neighbors but one choice left. You have no choice. So in other words, if V equals to this pre-image comes in position R in D, then d tau sigma of U, this is U, equals to d minus R plus 1. Okay, that's what it means. Once again, if you come in position 1, if this guy is ranked 1 in this position in tau, that means nothing, all its neighbors is never being used. It's used by later vertices. R equal to 1, used by later vertices, that means you have all D choices, all the neighbors are available, so on and so forth. Since this position of U equal to sigma inverse of Ui is uniformly sampled over all positions in D, we have this d tau sigma of U is uniformly sampled over 1D. It's also over D, right? Finishing the proof. It's not hard. it's easy to get confused here. Draw some pictures and analyze how exactly is this d tau sigma measures. Well, what exactly it counts, right? Any question? Okay, if there's no question, we're going to move on to a different set of applications about graph homomorphisms. So let's first recall.
Okay, I have a question. Can I ask a question?
Yes.
Uh, uh, can di be a function of n or sequence of degree, or just can be constant?
It can be anything. There's no restriction here.
Okay, okay.
Yeah.
Thanks.
Good. All right, so let's summarize this proof. This proof is actually not so long. Modular this claim, which is basically saying when you introduce another layer of randomness, then the number of unused neighbors is distributed equally likely from between 1 to its degree. So this one, I got confused a little bit, but if you look at this picture, it should be clear, and check this proof on yourself. Now, modular this claim, the idea is simple. We want to upper bound the cardinality of the set of all perfect matchings. What we're going to do is randomly uniform and random sample an element from this set. We associate its size to the entropy, which is log of the size. So this is what we want to prove. To bound the entropy, we view this perfect matching, which is basically a permutation of the right-hand side. We view it as the vector of images of where each vertex ui is mapped to. So this length n vector, random vector. We can use the chain rule to expand this vector. For each one of these conditional entropy, we realize that if you review all the previous choices of where U1 and U2, U3 is mapped to, then when you map U3, you cannot map it to the two vertices that U1 and U2 are mapped to. So in other words, this random variable takes value over the set of all neighbors that are unused so far. But the number of unused neighbors itself is a random variable. We have to analyze. So for this conditional entropy, using the definition of conditional entropy, this is n the maximality, is at most the expectation of sigma log of this range, size of the range of where x can take value, right? This is the range of x. Good, that's just maximality. The clever bit is that this size of the range is the number of unused neighbors. It's hard to analyze for a particular tau, but it's easier to analyze if you take tau, also random, introduce another layer, randomness, and then we can then estimate this guy through its expectation. This is what this claim is saying. If tau is uniform random chosen, then the number of unused neighbors is anything between 1 to its degree, and they happens equally likely. We can then analyze this much, much easier, and the rest are just computation. All right. Sidorenko's conjecture. So let's recall what is a graph homomorphism. A homomorphism from a graph H to a graph G is a map. Is a map from the vertex set of H to the vertex set of G. That preserves adjacencies. What it means is that if the pre-image are adjacent, then the images must be adjacent in G as well. So if UV are adjacent in H, then FU, FV must be adjacent in G. We're going to use this notation, home of HG to be the set of all homomorphisms from H to G. And little home of HG to be the cardinality. All right. So let's look at a simple example. If H is just an edge, you take arbitrary. What is this? This is the set of all maps that from the vertex set of V2 to vertex set of G, right? So you have an edge, this is K2, this is my G. This guy get mapped somewhere, this guy get mapped somewhere, and we require that there's an edge in between them, okay? Look, this guy can also map here. This guy can also map here. That means for every edge of G, it corresponds to two mappings F where the adjacency are preserved. So the set of homomorphisms from K2 to G are exactly the set of labeled edges in G. So XY and YX are both an element. XY and YX are both an elements in this home of K2 to G. So this is the set of all labeled edges in G. It's the same. Well, I shouldn't say equality. There's a one-to-one correspondence between this and the set of all labeled edges. Let's also normalize it to get some sort of density notation. So the homomorphism density, or this is homomorphism density, of H in G, we also call it H density in G, is nothing but, let's denote it by THG, is the total number of homomorphisms from H to G normalized by the total number of maps. What's the total number of maps? Each vertex in H has G choices, and we have to multiply for all vertices in H. So it's number of vertices in G, that's the choice of each vertex, to the number of vertices in H. That many choices, that many one we have to decide. So it's VG to the VH. Okay. Now, but in particular, we're gonna use this shorthand notation for when H is K2, we call it edge density. Which is what? 2 times, as I said, number of homomorphisms from K2 to G is 2 times the number of edges in G, the labeled ones, divided by, let's say our graph G has n vertices, n square. Okay. Sidorenko's conjecture says For any bipartite H graph, random graph with the same given H density, random graph minimize the H density. In other words, if I have a bipartite graph H, then for any graph G, we have the H density in G is minimized, is at least the H density in G raised to power EH. Okay. If we have a random graph where every edge is added with probability P, so this is our edge density P, right? And what's the expected number of copies of H in G? Well, for every edge H, you need to have an edge presented there. That happens with probability P. You take all the products. That's the probability a fixed set of vertices induce a homomorphism of H. So the right-hand side is the homomorphism, H homomorphism density in random graph. Good. This conjecture is still open. We're going to prove a special case using entropy method. We're going to prove a very baby case. Let's first reformulate it. So instead of writing the density version, let's write homomorphism version, equivalent form. So let's write P equals to the H density of the host graph. H density. Let's write V of H to be the number of vertices in H. Okay, then this thing is equivalent to the number of homomorphisms from H to G is at least n to the VH times P to the EH. Okay, this is because THG is what? Home HG divided by n to the VHG, right? So you want this to be at least P to the, in this notation, EH. Now just move this to the other side. That's this formulation. We're going to prove it for a very, very simple graph that it's a path of length 2. We're going to prove Sitorenko for this graph. This graph is so special and simple. I think it's good to illustrate the method. You can view it as a path of length 2. You can also view it as a star of size 2. You can also view it as complete bipartite graph with one part of size 1 and the other part of size 2. So this method, entropy way, is not the shortest way to prove entropy, to prove Sitorenko's conjecture for this particular graph. But it's amenable. It's very easy to extend it to prove. You extend the method here to prove all trees, because this is a tree, and stars, including stars, all trees and complete bipartite graph. So, so our goal is to show this is, let's view it as complete bipartite graph K12. Our goal is to show homomorphism of K12 to G is at least n to the power of n is the number of vertices in H, which is 3. P to the power of P, H density, is the number of edges in H, which is 2. So this is our goal. So there's someone asking, what's the inference of the bipartite property in Sitorenko's conjecture? Well, first of all, this conjecture is false when H is not a bipartite graph. Why bipartite graph is I don't know. Your question is essentially equivalent to the conjecture itself. Basically, why bipartite graph suddenly makes this inequality correct? I feel like because bipartite graph is basically blow up of an edge. You blow up an edge, you get all bipartite graphs, at least as a subgraph. So yeah, what you're asking is essentially the same as what Sitorenko is asking. So what's the special thing about bipartite graph? So we have this inequality. Okay, so how do we prove this Sitorenko's conjecture for K12? So look, first of all, this is basically the cardinality of the set of all homomorphisms of K12 to G. We know how to associate the cardinality of the set to entropy of a random variable. If you uniformly random sample something from the set of all homomorphisms, then this is just the log of that thing, right? In this case, we don't have to uniformly random sample something from here because we are proving a lower bound. So if we just come up with some distribution, some random K12 in G, then the entropy of this random K12 in G is at most the entropy of a uniformly chosen one, which is linked to the log of this homomorphism, number of homomorphisms. So all we need to do is to come up with a clever choice of random K12 in G and prove that this clever distribution has entropy at least this much. Then by maximality is at most this guy. All right. And how we're going to sample is the following. First, let me write the exercise for you to do. Here's the exercise, and we're going to use this exercise in this proof, is that the following two ways to sample edges are equivalent. The following two ways to sample edges in a graph are equivalent. The first way is you uniformly at random sample a labeled edge in G. Uniformly randomly sample edge xy labeled edge. The second way is we think of a uniformly randomly sampled edge, labeled edge. What does this mean? That means you have G, right? You have this edge, little x, this little y. So for all label edge xy, yx, x prime, y prime, y prime, x prime, they are equally likely to be this random label edge xy. That's what it means. Very simple. Among all 2 times E of G many choices, you pick one. It's equivalent, think of it as a 2-stage random process. Think of it as equivalent to first randomly sample X, the endpoints of a vertex, the first vertex, proportional to the degree of each vertex. What does this mean? That just means if you have a graph, we know that the sum of degree, right? And for each vertex v, you sample vertex v as x with this probability. So this means probability that x equals to v equals to degree of v over sum of all degrees. Now, after sample x proportional to degree, you sample y uniformly from a neighbor of x. Okay? Prove that these two are the same, which is intuitive also. Now we're going to show that Sidorenko for K12. In other words, we're going to show that homomorphism of K12 G is at least n cubed p squared. This is what we're going to show. Okay, we're gonna, as we said, the strategy is we're gonna define a random K12 and prove that this distribution of random K12 has entropy at least this much. Then using maximality is a most step. We're done. So that's how we, this is how we sample sample a random homomorphism. Let's view this homomorphism as x, y, z as a vector from the set of all homomorphisms K12 G. Okay, x, y, z are the image of the three vertices in K12 in G. Sample random homomorphism. How do we sample it? Two-stage process. First, we sample a labeled edge xy uniformly random, which is this guy. Uniformly random, sample a label edge xy. After you sample that, let's draw a picture. After you sample that, now we're gonna choose a uniform random neighbor of x as z. After you choose xy, x is fixed, right? Now in the neighborhood of x, we uniform random sample a z. We're gonna sample some z here. The key observation here is that conditioning on x is fixed. So this random distribution, conditioning on x is fixed. Y and z, they are identically distributed. If you fix x by this exercise, right? We sample xy as labeled edges uniformly random. which is the same as saying we sample x according to some distribution, which is this distribution, proportional to degree. Okay, fix x, then y, after fixing x, is uniformly distributed over nx, which is exactly the same as distribution of z, conditioning on x. So by the above exercise, we know that y and z, they are independent of each other, conditioning on x. If x is fixed, they just same IID copy of each other. Y, z are independent. Independent. Actually, they have the same distribution. And also, if you just look at xy and if you just look at xz together, they also have the same distribution. They are uniform random label edges. Okay. What that means by maximality, the entropy of xy and entropy of xz are the same, is the log of the range where they take value. The range is 2 times the number of edges. Is label edges is basically the set of homomorphisms from K2 to G, as we said, which is log of n squared p. This is definition of p. Okay, now we can write, we are done, basically. Let's look at the entropy of this random K12. This is entropy of this random K12 homomorphism. By maximality, this is maximality, is at most log of the size of the space of, by maximality is at most entropy of a uniformly chosen K12. But the entropy of a uniformly chosen K12 is homomorphism of K12 to G. Okay, this is maximality. But what is this? By chain rule, let's expand it, is h of yz given x plus h of x. Okay, why do we write it chain rule like this? Because if we given x, y and z are independent here, right? This is conditionally independence, means we can split the first one as the sum. Oops. Okay. Then by chain rule again, the first one is the joint entropy minus the entropy of x. The second one is joint entropy minus the entropy of x. The last minus cancel out with this guy, we have this. And we know both xy and xz, they distribute it uniformly over label edges, is this guy. So we have 2 times the log of n squared p minus entropy of this guy. But entropy of this guy, again, by maximality, entropy of X is at most log n, because X is a random vertex. Range is of size n. So minus log n. How do I do this? This equals to log n cubed p squared. That's exactly what we want to prove. Okay. Log of this is log of n cubed p squared. Here I give you an exercise. Extend the argument here to show that to prove Sidorenko for star. So think of this way of proving the star. Generate a random star of size b in an n vertex graph G as follows. First, sample the center vertex. Proportional to its degree, proportional to degree. And let it as center vertex, as a center. Let me to write this. Now we sample the leaves. Sample x1 xb in the neighborhood of y, uniform and random. This will give you a distribution over stars. Prove that, show that h of y, this entropy of this random star, is at least log of n to the b plus 1, p to the b, where again p is the edge density. Okay. Maybe next week we'll announce some set of homework problems. So for the homework, you need to submit it. The exercise, you don't. Okay. And here are more exercises. Try to prove, extend the argument here with C for K12, and prove it for two other cases. Prove Sidorenko for P4, the forward length 4 path, and C4. I would like to, which is K22. That concludes for today. Any question? Okay, if not, thanks for listening. I'll see you guys next week.